Welcome to the NET question solution, December 2025. In this presentation, we have mainly discussed regarding the suggestion for NET 2026 along with the organic chemistry solution. Myself, Dr. Shubhankar Samanta, Associate Professor of Jhargram Raj College, wish to present the NET question solution 2025, which had been held in the December 2025. The first question is the hydroformylation reactions. What is the hydroformylation reaction? Hydroformylation reaction is the reaction between that of the alkene with that of the formyl group. That is the incorporations of the formyl group in the presence of the carbon monoxides. Here, the carbon monoxide can be incorporated in the alkene system to give the formyl derivative, and this using this methodology, the different type of the alkene source has been used. Among the alkene source, the most electron-rich alkene source will participate in the reaction with higher rate compared to that of the less substituted alkene. Here, the more substituted alkenes gives higher rate, and that has been decreased proportionally with the lowering the substitutions of the alkene systems. And this similar type of the carbonyl group incorporations has been described in the Cladon group, where the iron tetracarbonyl complex has been used for the formations of the carbonyl compound by the alkyl substituents in the presence of the alkyl bromide. Here the catalytic cycles 18 electron rule is mostly maintained, and here the simple SN2 reaction has been happened. And this problem has been come from that of the reaction of the carbonyl with the phenol. Here, the carbonyl group can undergo intermolecular hydrogen bonding with the phenol. The question is that the correct match of the ketone column A with K equilibrium value with column B for their hydrogen bonding with phenol. Here, the phenol and the carbonyl group undergoes hydrogen bonding via the polarizations, and the driving force for the polarizations is the gain of the aromaticity. Here the cyclopropene system undergoes polarization to give the aromatic compound, and the negative charge on the oxygen atom is highest, so it has higher equilibrium constant for the formations of the hydrogen bonding. But in case of the cyclopentadienone system, where after polarization 4n pi electron has been created, and this 4n pi electron is reluctant to form the aromaticity, that is, this is the anti-aromatic compound, so the negative charge on the oxygen atom is lower, and hence the hydrogen bonding equilibrium constant is lower, and it is 6.2. But in case of the proton system, where after the polarization the aromaticity is gained in the ring, and but the ring is larger in size, so the delocalization of the charge is lower, and hence since the delocalization is greater, so the charge of the oxygen atom is also lower, and it is the intermediate between that of the cyclopropanone and cycloheptane system. And this problem has been come by uh, the intermediate involved in the following transformation, uh, where the carbene is the species. In that case, the carbene has been obtained by the reactions of the silver salt of the benzoic acid in the presence of the triethylamine. Here, the diazonium salt undergoes eliminations of the nitrogen atom form the carbene intermediate, which under full prearrangement to give the carbene intermediate ketene intermediate, and this ketene intermediate undergoes intramolecular cyclization to give the desired product. So the intermediate involved for this transformation is the carbene intermediate and the ketene intermediate. And the option C and D is the correct option. That is, the C option is the carbon intermediate and D option is the ketene intermediate. Here, this screenshot has been taken from that of the Claydon group, where the similar type of the carbon intermediate has been proposed, where the diphenyl carbene is mostly exist in the triplet state, whereas the dimethoxycarbene mostly exists in the singlet state. Next problem is the related to the natural product systems, where the alkaloids and terpenoids analogs has been prepared by the natures, where the alkaloid, we know that the alkaloids are mainly contain the nitrogen atom, and this structure is nothing but that the cation. It has been present mainly in the chocolate, and these alkaloids contain the nitrogen system, and so this is the alkaloid, and the terpenoids is the subunit of the isoprene subunit, which undergoes polymerizations on the or the series of the reactions to give the different type of the carbocycle derivative, and this is the rearrangement has been happened for the formations of the camphor system, and this is the terpenoids and content, this is the similar to that of the camphor system, and the polyketides is one of the systems where the phenol compounds has been opened, where the acetyl coenzymes was produced in their case, and we get the mainly the polyphenolic systems, and this is known as the polyketide. Next is the problem related to that of the NMR spectroscopy. In that NMR spectroscopy, where the different protons has been resonated in different field. Here the two methyl proton resonate at 0.95 delta, and it is splitted by the hydrogen atom as a doublet, and this methyl group adjacent to that of the carbonyl group resonate at 2.10 singlet 3H, and this hydrogen atom appear as a multiplet. It is the next to that of the carbonyl group. Here this hydrogen atom is more desealed compared to this hydrogen atom. This is due to the sigma bond desealing effect, and this sigma bond desealing effect also appear in the two butanone system, where the methylene proton is more desealed compared to that of the methyl proton. And similar type of the case here, this screenshot has been taken from that of the Pavia book, Labman Pavia, and from this book, this proton NMR is very much interesting for the where the fluorine can appear as a quadrate, and and with their Gator coupling constant. This is the correct order of the relative rate of the solubilities for the following compound in 80% aqueous ethanol at 25 degrees centigrade. Here the different type of the bromide substituents are present, where the rigid bromide is the A and the B, but after the formations of the carbocation, the rigidity has been appeared, and the positive charge is present on the bridging head position, which is contrary to our stability of the carbocation system, and comparatively less stable. Comparatively, these two bridging systems, this bridging system is comparatively more stable compared to this, due to the presence of the extra methylene group is present at the bridging head position, and this extra methylene group stabilize the bridgehead carbocation, but in case of the tertiary butyl carbocation, the carbocation becomes stabilized by the 9 hyperconjugating structure. So the tertiary butyl bromide has higher solubility rate compared to the bridgehead carbocation, and since the extra methylene group is present at the bridgehead position, so this carbocation is comparatively more stable compared to this. Hence, this has higher rate compared to this. So the rate of the solvolysis is C greater than A greater than B. And this screenshot has also been taken from that of the uh, Clayton group, where the perennial bromide has been prepared by the reactions of the HBr. By here, the carbocation is stabilized at the 3 carbocation, but here after conjugations, the perennial bromide is found exclusively, and this problem has been obtained in several competitive examinations. And this is the representation of the cyclohexane system in the dynamic form, where the 1s, 2r, 4s, 4 isopropyl 2 methyl cyclopropanol. We first designated the positions of the functional group, where the 4 position contain the isopropyl group and 2 position contain the methyl group and 1 position is the alcohol group. And after RS nomenclature, we can obtain that here the OH group has higher priority, then the this becomes 2, 3, 4, and the here 4 group present in the top position. So the according to the 1, 2, 3 clockwise 4 negative rule, this is the 1s configuration. Here also the 4 group present in the front position. So this is the 4f negative rule, and this priority sequence is given as the anti-clockwise rotation, and it gives the R configuration. Similarly, according to the Forbach positive rules, this isopropyl content chiral center is 4s. So the proper configurations of this is going to the option 2, and hence the correct option is the 2. And this screenshot has also been taken from that of the Clayton groups, where the cyclo propines cyclohexene system mainly exist in the half chair conformation, and after epoxidation it also exists in the half chair conformation. This is the preferable conformation. Similarly, if we get that of the 1,4-ditertiary butyl cyclohexane, the twist boat conformations is most stable compared to that of the chair conformation. Here the chair conformation becomes less stabilized due to that of the 1,3-dioxide interaction. This problem is the related to that of the heterocycles, where the major product formed in the reactions of indole with sodium amide and phenyl sulfonyl chloride. Here, the sodium amide can deprotonate the nitrogen atom, and the driving force of the deprotonation is the gain of the aromaticity. And this negative charge on the nitrogen atom is localized with that of the sodium plus ions, and it mainly attack to that of the sulfonyl chloride to give that of the N-sulfonyl derivatives. And these N-sulfonyl derivatives has been used for the protections of the nitrogen atom of the indole system. Here, this problem is related to that of the synthesis of the sedative drugs, that is the ketorolac. And this ketorolac has been obtained by the reactions of the intramolecular cyclization to give that of the ketorolac analog, and this problem has been came from that of the different competitive examinations. And this is the molecular orbital theory, the correct match of the statement about the bond angle of the CF3 radicals and CH3 radicals. Here, in case of the CH3 radicals, the fluorine contain the unshared pair electron, and this fluorine unshared pair electron can interact with that of the non-bonding single electron via the non-bonding sigma star interaction, and the non-bonding sigma star interaction is present in case of the CH3, and if we compare their bond angle according to their Bend's rule, the more electronegative atom occupy in the more p character orbital, and the more p character orbital is mainly obtained in the sp3 case, and where the p character is the 75% and the s character is the 25%, but hence the bond angle is reduced in case of CF3. But in case of CH3, due to the absence of their electronegative atom, the hydrogen atom mainly present in the more s character orbital. So the angle between that of the two hydrogen atoms is greater. So the CH3 has higher bond angle compared to that of the CF3. Next problem is the metallocarbene. Metallocarbene, this is the relate to that of the Schoch carbene and Fischer carbene. And this carbon atom, the spectroscopic related questions, where the carbon atom is that of the either alkyne or alkene. We are mainly know that in case of the simple alkene system and alkyl system, the alkene carbon is always resonate at higher chemical state compared to that of the alkyne carbon due to that of the diamagnetic anisotropic effect. We know that the alkene proton is always resonate at higher chemical shift compared to the alkyne proton. But here the phenomena becomes reversed in case of the metallocarbene system, where the alkyne carbon resonate at higher chemical shift. That is, the alkyne carbon is resonate at up to 252 ppm to 400 ppm, whereas the alkene carbon resonate at 202 to 300 ppm. So the option 2 is the correct option. Again, we know that the bond length is of in case of the alkyne system is lower than that of the alkene system. This phenomena is similar to that of the general case, but here the chemical shift phenomena is is completely reversed, where the alkyne carbon resonate at higher chemical shift, alkene carbon resonate at lower chemical shift. This is the mass spectroscopic phenomena, where the different type of the bromide in case of the dibromo system and in case of the tribromo system. In case of the dibromo system, where the two most abundant isotopes are 79 and 81, and these two bromides may be present as the 79 peak. This becomes M, and one is the 79, another is the 81, another is the 81, another is the 79, and in this permutation combination we get the peak intensity equal to 1:2:1, and this mainly calculated by that of the A plus B B B whole to the power n theory, where the n equal to 2 in case of two bromide system. So the equation becomes A plus B whole square, means A square plus 2AB plus B square. Since the natural abundance of the two bromide atoms is same, that is the 1:1. So the A equal to 1 and B equal to 1. So according to this equation, we show that this becomes 1:2:1. And in case of the tribromo substituted systems, where the n equal to 3, so A plus B whole cube equation has been applied, and according to this equation we get if we put the abundance ratio, that is the 1:1, we get the intensity of the mass spectra m plus 2 m plus 4 m plus 6 as 1:3:3:1. Next is the radical reactions. In that radical reactions, there are different type of the dehydroxylation take place, and here the in presence of tributyl tin deuterated systems, in the presence of aza-isobutyl nitrile. Aza-isobutyl nitrile used for the generations of the radicals, and these radicals has been created to incorporate the deuterium atom. After the preparations of the radicals, tributyl tin radicals, which can attack to that of the sulfur system and produces a alkyl radicals, and then this alkyl radical can capture the deuterium atom to produces the desired product, and which is matched with the option 2, and hence the correct option is the 2. Similarly, this screenshot has been taken from that of the Carothas books, where the different type of the Barton reactions has been taken from the radical pathway, where the different type of the alkyl nitride derivative, after cleavage of this O-N bond, we produces the radicals, and these radicals can capture the methylene proton, and after that the nitrosonium ion is formed, which under isomerization to give the oxygen derivative, and this oxygen derivative under Beckmann rearrangement we get the result product. This problem is very much interesting. Similarly, the cascade type of the cyclizations has also happened in case of the tributyl anhydride in the presence of the as a isobutyl nitride. Next is the stereochemistry problem, where the different type of the trihydroxy substituted butane system uh, can pentane system. This is the trihydroxy pentane system, where the optically inactive isomer after permutation combination we get the two isomers, and optically inactive isomers is the two isomers after permutation combination. Next is the reduction problem, where the different type of the amino acids, this is the alanine, phenylalanine, and this phenylalanine after reductions of the carboxyl group we get the alcohol derivatives. In the presence of the boron, the diboron has been used for the reductions of the carboxylic group, and it is more susceptible for the reductions of the carboxyl group, and hence it gives that of the alcohol derivatives. Similarly, lithium aluminum hydride is the stronger reducing agent, which can also reduces the carboxyl group to alcohol, and the sodium borohydride and zinc chloride is used for the reductions of the carboxyl group, where the zinc borohydride has been obtained by the reaction with that two reactive sodium borohydride and zinc chloride, and this also reduces the carboxyl group to alcohol. And this problem is very interesting, taken from that of the Carothers group. And here the reductions of the hydrogen with the palladium, and if the R group is the alcohol, then the reductions we get that of the cis product is 95%, and if the R equal to star, then we get the trans product. And here the chelation effect, that is the if the R equal to hydroxymethyl, then the chelate help to introduce the hydride to the top face of the alkene system, and we get that of the cis product as the major. And if we use the ester group, then we get the exclusively the trans product. Here, the correct sequence of the steps involved in the biosynthesis of the alpha terpene from linyl pyrophosphates, and actually different type of the biochemical transformations have been happened in the natures in our tree. So this is the sequence where the different type of the reactions has been happened, and here the linyl pyrophosphate after the intramolecular cyclization we get the six-member ring, and after the acid catalyzed cyclization we get the four-member ring and get the alpha pinene, and the intermediate involved for these reactions is the six-member ring formation with the loss of pyrophosphates, and then four-member ring formation, then the lose of the H plus. The whole sequence has been corrected, that is the A option, B option and C options are correct for these transformations. And this is the organometallic reactions, and this organometallic reaction, this is the reductive eliminations, and the reductive elimination mainly happen by their rate of the formations of the CC bond or the CH bond and this HH bond. In case of the reductive elimination is fast, very fast for the eliminations of the hydrogen gas, and reductive elimination for the formation of the CH bond is very fast, but reverse is not happened. That is the insertions of that is very slow. That is the forward reaction is fast, but the formation of the CC bond is very slow. Here the reductive elimination take place. There are the two type of the reductive elimination. It can happen by the formations of the CC bond or the formation of CH bond. But we know from this equation, it has been shown that the formation of CH bond is very fast compared to that of the formation of CC bond. So the methane elimination is more preferable compared to that of the ethane elimination, and hence we get the ethane as the product. Here, if the reductive elimination is not obtained, if the two eliminating group present in the trans orientation, and here the two eliminating group is the syn orientation, so the reductive elimination becomes happen. But if the two eliminating group in transition, then no reactions has been take place. Next is the point group related problem. Here the rhenium Cl6 2 minus, we know that the rhenium is mainly present in that of the dimeric form and via the quadruple interaction with the metal bonds, and from that of the metal, this is just like a square planar, and if we see that of the square planar point group, and we know that in case of the PTCl for 2 minus, the square planar point group is that of the D4H by the uh, symmetry present in that of the C4 along with that of the perpendicular 4C2, and the sigma H is present, and we get that of the D4H point group. Similarly, if we see that of the octahedral complex, cobalt diethylene dichloride complex, and in that case the C2 and the perpendicular to C2, and we get that of the D2H point group. So this is the point group of D2H and D4H. So the option 3 is the correct. Next is the organometallic problem. Here, this is the titanium isopropoxide, tetra isopropoxide has been used in the presence of the diethyl zinc. Here the titanium isopropoxide mainly undergoes chelation with that of the carbonyl group and activated the carbonyl group, and the ethyl group is transferred from that of the titanium to that of the carbonyl group to give the alcohol derivative. Here the bromine is remain intact. And similarly, this screenshot has been taken. This is the Kulinkovich reactions, where the titanium isopropoxide along with that of the alkene system in the presence of the ethyl acetate, we get the cyclopropanol intermediate, and this is very interesting, where the bromide is remain intact, and we get this type of intermediate where the two negative charge is created, and this help to form the cyclopropanol intermediate. And this is the dihydroxylation reactions, where the cis alcohols has been obtained, where the mainly the osmium tetroxide has been used, and the methyl group is present in the upside, so it is preferred to chelate at the downside and get that of the hydroxy group in the cis alcohol, and we get the sterically less hindered cis alcohol, and this is the reactions where the osmium tetroxide in the presence of the timida, we get the cis alcohol, all cis alcohol is the major, along with that of the minor amount of less substituted, less sterically hindered position. Protection chemistry. Here, the correct assignment of the following reactions. We know that the diethyl intermediate and this diethyl intermediate has been deprotected in the presence of mercury chloride and calcium carbonate. Here, the mercury can deprotect to that of the 1,3-diethyl intermediate and to get that of the carbonyl compound. This is the aromatic substitution reactions, where in the aromatic substitution reactions, phosphor undergoes ipso substitution by the eliminations of the cyanide, and we get that of the ipso substituted by the formations of the CP bond, and the options 1 is the correct. Next is that of the elimination reactions. In that elimination reactions, here the phosphorus can open the oxygen atom by the cleavage of the CO bond, and here the trans orientation has been obtained, and this trans orientation undergoes rotation to give that of the cis orientation. A Packard type of geometry has been formed, and this Packard type, after elimination of the phosphine oxide, we get that of the trans alkene. Next is the heterocycles. In that heterocycles, where the 3 positions is more reactive compared to that of the 2 positions, after the intramolecular reactions, we get the intermediate B intermediate, and a spiro type of intermediate is been obtained. And after the migrations of the alkyl group, we get that intermediate, and this after aromatization, we get that of the desired product. So the intermediate A and B is the correct intermediate. Next is the sequence of the reactions where the conjugated additions take place with that of the nitrogen atom, and after that the phenyl group can added the 1,2 additions, and oxygen negative charge is attacked with that of the diethyl carbonate, and after the eliminations of the ethyl group we get the desired product. And so the options 3 is the correct options. Next is the co-reagent. Here the intermediate has been obtained by the three by the reactions of the nitrogen fluorine pair with that of the cleavage of the CO bond, and we get a intermediate, and this intermediate after the chair conformations and after the intramolecular cyclization we get our desired product, and the options 3 is the correct option. Next is the Canniger reactions. In the Canniger reactions, the deuterium exchange has been take place by the reactions of the intramolecular hydride transfer and intramolecular hydride transfer. Here the this hydrogen atom is mainly participate for these reactions, and the deuterium exchange only take place with that of the with the that is the deuterium only carboxyl part, but not for the alcohol part. And options 2 is the correct option here. The alcohol part, the deuterium cannot take place due to that of the absence of the deuterium hydrogen atom with the in the starting material. Next is the interaction. This is the intramolecular interactions, and after the formations of the 6-member cyclic intermediate, we get the this product by the 6-member chair conformation, and this is the interesting reactions for the intramolecular interactions, and this has been taken from the Carothers group. And this is the electrocyclic reactions where the intramolecular conversion reactions take place in the presence of the where the B is the option is the correct option, where the dissociatory ring closing we get the this product, and D is the correct option where this dissociation only take place in under photochemical condition. And this is the aromatic substitution reactions where the aromatic, this is the ipso type of substitution, and after the ipso substitution by the eliminations of the 3-degree carbocation we get the isobutane intermediate, and the option 3 is the correct option. Next is the stele coupling where the palladium can undergo stele coupling in the presence of the tin in the palladium, where the transmetallation take place by the interaction of the palladium with the tin, and then CC bond coupling by the reduction elimination we get the desired product. And this is the reactions of the cycloaddition reactions where the intramolecular proprise to cycloaddition after eliminations of the hydrogen cyanide we get that of the desired product, and option 2 is the correct. Next is the electrophilic aromatic substitution reactions where the concentrated H2SO4 has been used to protect the para positions of the phenol rings, and after the halogenations we get the 2-bromo phenol derivative, and the deprotection take place in the presence of the sulfuric acid. And this is the formations of the tryptamine derivative by the reactions of the this is the Fischer-Indole synthesis, where in the Fischer-Indole synthesis 3 sigmatropic C2 will occur, and after the intramolecular cyclization and the eliminations we get the tryptamine derivatives, and this problem has been mainly come from that of the heterocyclic group, and this screenshot has been taken from that of the Clayton groups. And this is the NMR spectroscopy, and this from this NMR spectroscopy this is the Karplus equation has been applied here. Here the phosphorus and hydrogen can coupling with this, and here the phosphorus can couples with the hydrogen, and can phosphorus couple with axial hydrogen or in the equatorial hydrogen. In case of that, we know that the axial coupling constant is large. Always the higher coupling constant is splitted first, then subsequently lower coupling constant. Here the angle between that of the HA and PC is 180 degrees, so it first splitted as a doublet, and then the angle between the HA and HB is 90 degrees, so splitted is later, and hence The first the filter is a doublet and the doublet is treated as a triplet. So the option one is the correct option. That is the this is the doublet of triplet. Next is the Shapiro reaction. In that case, the Shapiro reactions has been happened by the at first the this is the diethyl azodicarboxylate dead, and it has been happened for the formations of the carbonyl group by the activation of the oxygen atom and to give the carbonyl group, and after that the azo compound is formed, and this azo compound is helped to form the exocyclic bond, and this option 4 is the correct option. This is the uh, this problem is very large problem, but the phenomena is very simple. This is the reactions of the peroxide with that of the aldehyde group to form the peroxy hemiacetal intermediate, and then the eliminations of this peroxy hemiacetal intermediate to get the desired product. So the nucleophilic attack and the peroxy hemiacetal and the elimination of formate anions is the correct option. Next is the oxidation product. This is the Jacobson-Katsuki catalyst, and this Jacobson-Katsuki catalyst will be used for the epoxidations of the alkene system in the presence of sodium hypochlorite in the DCN and 4 degrees centigrade. And the correct option of this catalyst is the 3, and this catalyst has been taken from that of the Parathas group. Next is that of the Weicker oxidation. In the Weicker oxidation, different type of the intermediate has been formed. One is the palladium ethylene intermediate, another is the palladium beta hydroxyethyl intermediate, and palladium vinyl alcohol intermediate. So the option one is the correct option. Next is the which one is the Ramon active and which one is the IR active. We know that the linear molecules is always either it may be Ramon active or Ramon active. In case of the volume has been changed, the molecules becomes Ramon active. This is the non-linear molecule, so the volume always has been changed, and so the any type of stretching mode is the Ramon active. But in case of the ozone system, the dipole moment has been changed during vibration, so the it is also IR active. Again, the it contains the C2V symmetry, so the options A, B, and D is the correct option. And if we consider the molecular orbital theory, from this molecular orbital theory, this is the one type of the allylic anion system. So the highest occupied orbital must be a diamagnetic, so it is a diamagnetic molecule. And this has been corrected from that of the previous 2025 June questions. For the where the deprotections of the block protecting group is aluminum chloride dichloromethane, and aluminum chloride is the acidic one and in the presence of the dichloromethane. And actually this problem is previously described as the option 2 is the correct, but it has been thanked on the for my sir Dr. Satyajit Dey and Dr. Shubhajit Ghosh for this corrections. That is the aluminum chloride and dichloromethane is the correct option, and this has been taken from a book where the work has been deprotected in the presence of the acidic medium. Thank you for watching my